Wow, it's been pretty exciting this morning over here. So I had a window open, and in the morning, the cat I'm watching, Ivan, is really loud because he wants food. So he's going wow 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 wow, and then um, and then through the open window, there's a response wow. So this other cat goes wow, and it's in the backyard. The other cat's in the backyard. So then I let Ivan into the backyard, and the other cat runs away. Okay, so then I go to walk my dogs, um, as I do in the morning. And when we're on the way back, I see the cat trying to get back into the backyard to interact with Ivan. And so that was very exciting. And as that was happening, two coyotes come running down the street, like big coyotes, not, sometimes you see a coyote and it's like all, it does not look healthy. Like these two coyotes looked healthy, like well fed. They run down the street. That causes the other cat to run away. Okay. And then Bug is trying to get the coyote, one of the coyotes. And so then I come back inside. I teach my first period class. And then I go back outside in passing period just now. And the cat is back in the backyard and interacting with Ivan. So it's very exciting. It's been a very exciting morning for the animals in the Pettibone household. And I'm kind of worried because Ivan doesn't know how to jump the fence. He doesn't understand. And he definitely saw the other cat jump the fence. So I'm worried he's going to realize that he can jump the fence. So I'm trying to watch him closely today. And now the other cat left, and they're both on either side of the fence, just kind of like meowing at each other. It's pretty funny. This other cat is like more of a Garfield, like a round face cat, and it looks like he weighs about twice as much as Ivan. Okay. Very exciting. Wow, that's a powerful description of coyotes. All right, so this is SL 225. Cool. So what we are going to be talking about today is something called electrical power. Okay. So if you recall, power is work divided by time. All right? Power is work divided by time. Oh, by the way, there was a before I go too far in this lesson, I remembered there was another ohm pun that someone came up with. Okay, so I'm going to do this one. And type it into the chat if you know what it is. Who knows what that is? Maybe I need to draw a little bit more. Maybe I'll put a little there's this magnifying glass. So this is Sherlock Ohms. All right, very good. And I have a follow-up after this lesson. There's a great follow-up. So thank you for that. So this is Sherlock Ohms. All right. Okay. So don't let me forget. Once I look like I'm about to end the lesson, make sure, tell me to go back to this because I have a follow-up that's really good. Okay? All right. So remember, work is a transfer of energy. So the energy is going to go into something. All right? Now with electrons that are flowing around a circuit, like for a battery, for example, the work that a battery does is giving the electrons potential energy. So this work becomes potential energy of the electrons. Okay? So I'm going to write this as delta U over delta T. Okay? And then I'm going to take this and I'm going to multiply it by Q over Q, Q being charge. So now I have delta U over Q times Q over T. Okay. So delta U over Q is the definition of electric potential difference. Charge per time is the definition of current. Okay? So what that gives us is an equation for electrical power, which is I times V. All right? So an important point, some devices, so this P can represent power output or power consumed. All right? So if we were talking about power, so some devices output power, for example, a battery, as long as the battery is not being charged. If the battery is being charged, then it's actually receiving power from something else. Others dissipate or use power. So, for example, a light bulb, which is essentially a resistor, or a motor, an electrical motor. All right. So, we can actually, so this is the equation for power, and this equation applies to anything. Any circuit any circuit element, okay? But we can talk about, or we can, I'm going to say, combine this with Ohm's law, okay? So remember, Ohm's law says that V equals I times R, and so if we wanted to, we could replace the potential difference here with I times R. So we could also write it as I times IR, in which case we get another equation for power, which is I squared R. So this is another formula for electrical power. Or we could replace the I with V squared, or sorry, with I equals V over R, so just by dividing both sides by R in Ohm's law, then we would get V over R times V. So I've replaced the I with V over R, and then I get V squared over R. So these two apply only to resistors. All right? These apply only to resistors. So, we could do a little circuit here. Let's do some examples. I'm going to do an example that is sort of similar to what we saw in the quiz. So this one looks a little confusing. So maybe this is 3 ohms. Maybe this is 3 ohms. And maybe this is 2 ohms. And maybe this is a 12-volt battery. Okay? So, and we want to know, what is the power output of the battery? All right. So because it's the power output of the battery, we want to use IV, because I squared R and V squared over R, those are used. Why can't I? Because my camera is a little bit weird today. So you can only use these for a resistor, calculating the power dissipated by a resistor. But this equation applies to any circuit element. What we're going to do is we got to find the total resistance. All right. And so it doesn't look like anything is in series or parallel, but actually the 3 ohm and the 3 ohm are in parallel. Okay. How do I know that? Well, you could imagine, remember, wires are flexible. They are bendy. So you could imagine taking this wire with that resistor and pulling it over to that side. Okay? So that would take this and pull it over to this side like that, and then we've removed it. So wires are flexible. And then I think it's pretty clear that these two are in parallel. Okay. Another nice way to check if two things are in parallel is if you can make a loop in the circuit that only has two things in it. So for example, if I walked around the circuit like this, I only encounter this resistor and that resistor. So if you can do a loop in a circuit where you only encounter those two things, then those two things are in parallel. Okay, so I could do a loop here where if I do this loop, then I only encounter those two resistors, so they are in parallel. You can't do a loop in the circuit that only has, oh, I guess I can in that case. Let me put another resistor here. So if I try to do a loop that only includes these two, I can't do it, because if I try to walk around through this resistor and then through that resistor and come back around, I have to hit this resistor. So these two resistors are not in parallel because I can't make a loop that just has the two of them. So that's, if you have a confusing looking circuit, using that loop method can help you see when two things are in parallel. So I have these two 3 ohms are in parallel. So 1 over R sub P equals 1 over 3 plus 1 over 3, which is says that R sub P equals 1.5 ohms. Fun fact, if you have two equal resistors in parallel, the total resistance will be half. So half of 3 is 1.5. So I redraw my circuit. So I have this 2 ohm resistor, and then these two combined to make a 1.5 ohm. All right. Then these are obviously in series, so that they will combine to make 3.5 ohms. So the total resistance of this circuit is 3.5 ohms. So then I can calculate the current as V over R, so that would be 12 over 3.5, which is 3.42, 3.43 amps. And then I calculate the power as P equals IV, so 3.43 times 12 gives 41.1 watts as the power. Okay, 41.1 watts is the power output of the battery. I guess I'll give my other pun here, right? And so I realized I was going to be talking about electrical power in the next lesson after I gave my ohm puns. And someone said Sherlock Ohms, and then I was like, wait, well, what does Sherlock Ohms say? He says, elementary, my dear Watt son. Aha! Sherlock Ohms says, elementary, my dear Watt son. Okay, I thought that was really funny when I thought of it. So I hope that gives you a chuckle. I hope I made you chuckle. All right. So let's talk about some other ways you can use this equation. So let's suppose that you had the battery is just connected to a single resistor, okay? And this is a heater, okay? So maybe this resistor is heating up some water. So let's say this is a 12-volt battery, and then let's say that this is a 4-ohm resistor. So the power dissipated by the resistor is going to be V squared over R. So that's going to be 12 squared divided by 4. Okay, so what, 128 divided by 4? $36 watts is the power that's going to be dissipated by that resistor. Okay, so now it's heating some water. Let's say it's a heater heating 1 kilogram of water. All right, so now what we do is we can connect this with other areas of physics. For example, we can connect it with calorimetry. So this power is the heat that goes into the water per time. Okay? So the heat that goes into the water is going to be MC, change in temperature, divided by the change in time. Okay? So uppercase T represents temperature, lowercase t represents time. So now we're using the electrical power to figure out what's going on with the water, because this resistor is dissipating heat that's warming up the water. So we have 36. The mass of water is 1 kilogram. The specific heat capacity of water is like 4,200 or so, times change in temperature over change in time. Okay. So we have 36, 4,200. So 8.6 times 10 to the minus 3 Kelvin per second is the rate at which the temperature of the water will increase. So that's kind of cool. You could calculate things, and so you're calculating essentially the rate of temperature increase of the water. Now this applies equally well to things like air. So if you have a heater and you know what the power output of that heater is, you could calculate the rate of temperature increase of the room by figuring out what is the mass of all the air in the room, what is the specific heat capacity of air, and then knowing the power consumption of your heater, the electrical power consumption. So that's pretty cool. Let me give you another example. What if we had, again, a 12-volt battery, and again, it's a 4-ohm resistor. But this 4-ohm resistor is a motor lifting a 2-kilogram mass. All right? A motor lifting a 2-kilogram mass. So in this case, the power that is consumed by the motor is the power that's going to go into the mass. Okay? So this power is going to be equal to the gravitational potential energy gained by the mass divided by the time elapsed. Okay? So power is kind of the way that you connect circuits to other areas of physics, because now that power, that electrical power, is being converted by the motor into gravitational potential energy. Okay, so and a motor from the perspective of a circuit is essentially a resistor. So the gravitational potential energy gained is going to be mg delta y. All right. So the actual power, this is the exact same circuit as before, so we still get 36 watts is the power used to lift the 2 kilogram mass. So I have 2 times 10 times dy dt. All right. So then divide both sides, and we get 1.8 meters per second is delta y over delta t. All right, so if you had this motor connected to this battery, lifting that mass, it would lift it at roughly 1.8 meters per second. That's assuming 100% efficiency. So typically speaking, you know, some of the energy, some of the power that this motor is consuming is going to go to heat generation. Okay, so you have a certain efficiency factor that you would probably want to multiply that by. So some efficiency times that power equals the gravitational potential energy gained. All right. I did want to talk just really briefly about conservation of energy in circuits. So let's say you had, a circuit like this, like a simple voltage divider circuit, something like that. So this is resistor 1, this is resistor 2. So the battery is outputting power. And then the resistors are consuming the power. Now, if you just have a resistor that is not representing something more complicated, so if you actually had a physical resistors, all they do is they just turn that energy into heat. And they control current flow, so that's nice, but they turn that energy into heat. Again, if this resistor is representing a light bulb, then it's turning that power into luminous energy, the energy of the light waves. If it's a motor, it's turning it into, the energy of lifting something. If it's a heater, that resistor is generating heat that is warming something up. So anyways, the way conservation of energy works in a circuit is that the power that is being output into the circuit has to be equal to the power that is consumed within the circuit. Okay? So basically the power output of the battery is going to be equal to P1 plus P2. So the power output by the battery is equal to the power dissipated by the resistors. Okay? If that's not happening, then if you had more power being output than power is being dissipated, then the question is, what is happening to that energy? Okay, so the way that you conserve energy in a circuit is with these types of relationships. Okay, so that is my lesson today, and I will see you in the Zoom room.